Welcome to Part 2 of the lesson on Section 7.7, Indeterminate Forms and L'Hopital's Rule. In Part 1 of this lesson in class, you learned how to apply L'Hopital's rule to the indeterminate forms 0 over 0, infinity over infinity, and 0 times infinity. In Part 2 of this lesson, we'll look at how to apply L'Hopital's rule in cases of infinity minus infinity and the indeterminate powers 0 to the 0 power, infinity to the 0 power, and 1 to the infinity. Our first example is of type infinity minus infinity. Notice that the graphs of both y equals 1 over x and y equals 1 over e to the x minus 1 would have vertical asymptotes at x equals 0. In both, the graph approaches negative infinity from the left side of 0 and positive infinity from the right side of 0. So that's why we have infinity minus infinity. First, you should never assume that infinity minus infinity results in 0. In fact, this problem will be a counterexample of that assumption. When you see a limit of this type, first use a common denominator to subtract. Plugging 0 in for x, we now have indeterminate form 0 over 0, which means we can apply L'Hopital's rule. The result is still of the form 0 over 0. So let's apply L'Hopital's again. Plugging in 0, we find that the limit equals 1/2. And once again, notice that infinity minus infinity does not necessarily equal 0. In our second example, we'll find the limit of e to the x plus x raised to the 1 over x power. This limit is an indeterminate power of the form infinity raised to the 0 power. Although past experience would tell you that infinity raised to the 0 power should be 1, this does not necessarily have to be true. Again, this limit will serve as a counterexample to that assumption. Start by setting the expression equal to y, and then taking the log of both sides. Use a law of logs to rewrite the right-hand side. Next, we'll find the limit as x approaches infinity of the log of y. This is of indeterminate form infinity over infinity. Apply L'Hopital's. This is still infinity over infinity, so we'll repeat L'Hopital's. And repeat again. This limit is equal to 1. So the limit of the log of y equals 1. Since y is equal to e to the ln y, then the limit of y as x approaches infinity will be e to the first, or e. Now we'll revisit the limit of 1 plus r over n to the n power. In a previous lesson, we used a table on the graphing calculator to show that this limit is e to the r. And this was my explanation for the formula for continuously compounded interest. Now we'll use L'Hopital's rule to confirm this limit. If we let y equal 1 plus r over n to the nth power, then the log of y is equal to n times the log of 1 plus r over n. As in the last example, we'll use the limit of the log of y to find the limit of y. I rewrote the n in the numerator as a 1 over n in the denominator to make our limit of indeterminate form 0 over 0. Apply L'Hopital's. This simplifies to r over 1 plus r over n. As n goes to infinity, the r over n in the denominator goes to 0, so the whole expression goes to r. We just found that the limit of the log of y is r. So the limit of y, which equals e to the log of y, is e to the r. This concludes our lesson on Section 7.7, Part 2 of L'Hopital's rule.